Alright, last time we got into our last type of spectroscopy, which is called atomic spectroscopy, or AS for short. In this type of spectroscopy, we vaporize our analyte solution, breaking all the bonds and converting the chemicals into gaseous atoms. And gaseous atoms are simple to work with because the only types of transitions possible in them are electronic transitions. There are no bonds to vibrate anymore, no rotations to consider. It's just a simpler situation. So take, for example, sodium. Okay, sodium has a valence electron in its 3s orbital, and then that electron can typically be promoted to the following p orbitals. There are other orbitals in sodium, but these are the three excitations that happen appreciably. There are other orbitals and possible transitions in sodium, but these are three of the more appreciable ones. And as we've seen before, each of these transitions corresponds to a different light energy or wavelength being absorbed. Not all transitions are equally probable, thus this excitation right here happens more often than the others, and we see the largest absorption peak. Notice how much cleaner this looks compared to our previous molecular spectroscopy examples. We just have three different peaks. They're sharp and they're well spread out, and that's because they correspond to these different electronic transitions. We don't have this situation, where on top of the electronic transition we have these different vibrational transitions that are all closely spaced together in energy, and so along with just that one electronic excitation, we have all these different possible absorption peaks that we might see that are all closely spaced together, and when we're in a polar solvent, as we saw, we get everything merging together into this broad hump, and then we would see the same type of situation for all these other electronic transitions, which would also have accompanying vibrational excitations possible. And it becomes very convoluted. But we don't have this situation when we convert everything into atoms. We just have this situation. It's simple. Every peak represents a different electronic transition, and that's it. The peaks are sharp and narrow, and they're more spread out from one another than vibrational excitations. So that's why we would convert everything into atomic form. Now from there, we can potentially do an absorbance experiment, in which case we hit the sample with light and track the absorbance as electrons are excited. We would call this variation of the technique AAS for atomic absorption spectroscopy. Or we can track emission of light, in which case we would call this AES, atomic emission spectroscopy, where in this case we don't shine in any light. We rely on high temperature collisions to cause these excitations to happen in the first place, and then as electrons relax back down, they will emit these different wavelengths of light, and we can measure that. So we measure the emittance. Now, a general term for both of these signals would just be intensity, and that's what we'll typically be using in this unit, is we'll just say intensity, and we understand we're tracking the intensity of absorption or emission of light based on what technique we're using. Now, as for which one to use, well, we contrasted the major pro and con before. Let's recap that. It's really kind of like having to pick between two great choices on The Bachelor.
Hello, and welcome to a very special edition of The Bachelor, Sean Tells All.
Now, I'm having a really difficult time. I mean, on the one hand, emission's great because if I have a multi-element sample, all of them can potentially be excited by the flame and then emit, and it's simple, whereas with absorption, I would need to buy a separate lamp for every element. On the other hand, if the element's not excited by the flame in the first place, then there's no emission, and I can't use the technique, so I just didn't expect it to be this hard.
Take a moment, get your thoughts together, think about what you want to do tonight. When you're ready, come join us in the rose ceremony.
And so we have pros and cons, but there is one other difference between the techniques to address, and it's temperature related. So for the rest of the video, we'll cover that last piece of theory for atomic spectroscopy, and then in the following videos we'll get into actual analyses. Now these experiments take place at high temperatures, so next we need to discuss the effects of those temperatures, particularly on what are known as excited state populations and spectroscopy. So let's first write that title and then understand what it means. The effect of temperature the effective temperature on excited state population and spectroscopy. So what does excited state population refer to? Well, it just refers to the number of atoms that are in an excited state, or in other words, atoms that have had their electrons excited from the high temperature environment. And so its symbol is going to be N star. And what we're interested in is what is the ratio between the number of atoms that were excited in the fire versus the number of atoms that are still in their ground states. So we'll call this ground state population. And the reason why this is significant is because the number of atoms that are excited in the flame is directly proportional to the intensity of emission that we can see in an AES experiment. On the other hand, the number of atoms that are still in the ground state relates to the intensity of absorption in an AAS experiment, because atoms in the ground state are still able to absorb light and be excited, whereas atoms that have been excited by the fire are not going to absorb that light anymore, but they can relax and emit light. So again, excited state population gives us an idea of how much light can be emitted, and ground state gives us an idea of how much light can be absorbed. And this ratio relates to temperature. Again, higher temperature, higher energy collisions, greater chances that a collision might result in an excitation of an atom's electron. And so there must be some equation that relates this ratio to temperature, and here it is. This ratio is equal to, we're going to put a term in parentheses, which is going to be G star divided by G subscript O. We'll define that later. And then this term will be multiplied by e to the negative delta E over lowercase k and then T. So the delta E represents the difference in energy between two states, the ground state and the excited state of interest. The T, of course, means temperature, and little k is not something we've seen in this class, but in principle you've seen it before, but it's been a while. It's known as Boltzmann's constant. It is equal to 1.381 times 10 to the minus 23, and the units are joule per Kelvin. Notice the Kelvin. Our temperature must be in kelvins for this equation. Now, as for those G's that we wrote earlier, those stand for degeneracy. Degeneracy. Which means the number of states with equal energy. Number of states with equal energy. And so here's a quick example of what I mean by states with equal energy. Imagine that we had that lithium atom, where its high energy valence electron is in the 2s orbital, and we wanted to excite it to the 2p orbital. Well, there's actually 3 different 2p orbitals that it could reach, and each one of them is the same energy. And thus there are 3 potential excited states that it can reach that would be the same in energy as each other. Now things can definitely be more complicated than that, and so I will always give you the G star value, the degeneracy of the excited state. Will give. As for the degeneracy of the original ground state, well, we'll assume that's always 1. Assume equals 1. And that you just need to know, okay? So let's see this equation in action and call it a video. So here's our example problem. The lowest excited state of a sodium atom is 3.371 times 10 to the negative 19 joules higher than the ground state and has a degeneracy of 2. What fraction of atoms are excited from the ground state at 2600 kelvins versus 2610 Kelvin? Well, this is really just a plug-and-chug question, although we'll get into an important theoretical concept after I do it. So let's do 2600 in full. We'll start with that equation. We are interested in the fraction of n star compared to ground state population. And then this is going to be equal to the degeneracy of the excited state, which we're told is 2, over the degeneracy of the ground state, which, as we wrote before, is always going to be 1 in this class. And then multiply by the exponential, and then we have that negative sign, and then the delta E, the difference in energy. This is given to us in the problem, right? It's 3.371 times 10 to the minus 19 joules. And we divide this by the Boltzmann constant, which is 1.381 times 10 to the minus 23 joules per Kelvin. And then that's multiplied by our temperature, 2600 Kelvin. And we just plug all of that in, and we get the number 0.000167. So 0.000167. If I were to convert that into a percent, which is as simple as multiplying by 100, I would get 0.0167%. So that is the percentage of sodium atoms that are actually excited and capable of emitting light, which might seem like a very small percentage, but just like in fluorescence, we don't need much emission of light to reasonably detect it. So this could actually be a measurable signal. Now, if that temperature were to increase by only 10 degrees Kelvin, what do you think is going to happen to that excited state population? Will it go up or down? And do you think it will be a significant change? Well, as for the first question, hopefully your instincts told you that we will have a greater degree of excitation at higher temperatures. But is it a substantial increase in excitation? That's not as obvious. We need to work the math. So literally, we would just use the exact same equation as above, except instead of 2600, we would plug in 2610. And if we plug that all into our calculator, the fraction that we get is now 0.000174. Which still seems very small, and it is. But if we compare it to this number here, that's actually 4% larger than this number. So 4% increase in n star. That is substantial, and this is going to affect your emission signal if you're doing an AES experiment. This is what AES is based on. What AES is based on. If your temperature were to all of a sudden increase by 10 degrees in that fire, well then your signal is going to increase by 4% in an AES experiment. And that is a significant alteration that could potentially mess up your analysis. So it's very important that we keep temperature stable for AES. Let's write that note. T must be stable. T must be stable in AES, or intensity will vary. Or intensity will vary. Now you might be wondering, what about AAS? Does temperature affect that? After all, your instincts might be telling you that if this number increased by 4%, then this number must have decreased by 4%. So wouldn't that affect the number of atoms that are capable of absorbing light in the first place, which in turn would affect the absorption signal? And the answer is no, it doesn't quite work like that. So let me clear some space and quickly discuss the math behind this. In the example we just did, we calculated the ratio of how many atoms are excited versus how many atoms are left in the ground state at these temperatures. If we do some quick math and convert to percentages, we can say that 0.016% of these atoms are excited and the other 99.9833% are still in the ground state. We saw this number increase by 0.0007, which means that this number is going to go down by 0.0007. However, this number is so small that even that small increase actually corresponds to a 4% change. But this number is so large that going down by that small number corresponds to very little percent change. In fact, it's less than a 0.001% decrease in the ground state population, which is ultimately what AAS is based on. What AAS is based on. So that 10-degree change in temperature will have very little effect on an AAS experiment, but it is important to keep temperature stable for AES. Now this can definitely be confusing and not intuitive, so let me try to illustrate this further with a simpler example. So let's consider an overly simplistic situation where we only have 10 atoms, and that atom only has one higher energy orbital that electrons can potentially be excited to. And let's say that at some temperature, 9 of these atoms have their electrons in the lower energy orbital, and thus these electrons are capable of being excited. In other words, these 9 atoms can absorb light. On the other hand, one of these atoms has experienced a high enough energy collision that its electron has already been excited. This is not capable of absorbing light anymore, but it could emit it as it goes back down. From the population standpoint, we would say that the ratio is 1 to 9. Now let's increase the temperature, and let's say at this temperature, 2 of the atoms were able to have high enough energy collisions to have their electrons excited. So in this case, we still have 8 atoms that are capable of absorbing light and having their electrons excited, but at the lower temperature, we had 9 of those types of atoms. So that means that we've gone from 9 atoms that could absorb light to 8. That translates to an 11.1% decrease in our potential absorbance signal. But as far as our excited atoms go, well, we've just gone from only having 1 atom that could emit light to 2 atoms that could emit light. That's a 100% increase in emission signal right there. So that 1 atom changing from being in the ground state to an excited state has had a far more significant impact on our emission signal than the absorbance signal, which is in agreement with what was being stated in the previous example. Now, practically speaking, like in the previous example, there are far more than 10 atoms in a sample, and the fluctuations in temperature produce far less dramatic changes in both signals. But the fact is, AES will be affected significantly more than AAS by temperature fluctuations. And so let's see the practical significance of that in an analysis. Now this is one of these clickers that I'm actually going to solve in the video because it informs a lot of the remaining concepts that we will be discussing in this unit. So here we go. You conduct an AES experiment to study the lithium content of an unknown sample, and you start by making a calibration curve. Then as you begin to analyze the unknown, the temperature increases. What will be the consequence of this? Will the unknown concentration we calculate be higher than true, lower than true, or there's no way to tell? Well, let's think about this. So here's our calibration curve, and it works like every other calibration curve you've seen and done in this class. It's just measuring the intensity of different concentrations of standards and plotting a line through that data. And in principle, we then measure the emission signal of the unknown itself, plug it in, solve, and great. This should be extremely comfortable for you at this point. But now things are about to get uncomfortable because we're about to deal with something we haven't seen before, which is false readings. When we were analyzing the unknown, the temperature went up. And for the reasons we've already covered, we know that an increase in temperature for emission-based experiments will increase the signal. And so we're not going to measure the true signal, we're going to measure a falsely high signal, and we're going to plug that into our calibration curve and get a falsely high concentration of lithium, all because the temperature wasn't able to remain constant. In an AAS experiment, this wouldn't be a big deal for the reasons we've already covered. We'd still get the proper reading. But for AES, where that signal can appreciably increase with a temperature increase, we need to be concerned about this. And temperature stability is very important.